Hello, this is Math 2231 coming to you from the College Edu page during the summer of 2020, and this is the conclusion of the To Infinity and Beyond. At the end of the last segment I posed this problem, and hopefully you've maybe solved it already, but perhaps if not, you know what to do. Let's see how you did. In each case, you're going to be dividing top and bottom by x squared. And then when you take the limit for a, you're going to get 0. When you take the limit for problem b, you're going to get 2/3. And for c, you're going to get infinity. Now here, this note says you can conclude the limit does not exist because the numerator increases without bound while the denominator approaches 3. I understand what they're saying there, but this is a technicality we don't need to deal with. And so in our class, this answer will be infinity. It will not be does not exist. Thinking about this problem, you might say, gee, there ought to be a rule. And here is the rule. If the degree of the numerator is less than the degree of the denominator, that's the highest power of x that you see, then the limit of the rational function is 0. If the degree of the numerator is equal to the degree of the denominator, then the limit of the rational function is the ratio of the leading coefficients. That's the highest power of x. That would be common in this case because we're saying the degrees are equal. If the degree of the numerator is greater than the degree of the denominator, then I would not say does not exist. I would say that the limit would be infinity. And it'll either be positive or negative infinity depending on other characteristics of the problem. Here's a little bit of a math history footnote. One of the reasons I like to think about this is that I once was in love with a lifeguard named Gaetana. And this is Maria Gaetana Agnesi. And she was one of the very few women who were active in mathematics back during this day. And she wrote, in her early 20s, she wrote the first textbook that included both differential and integral calculus. There was an English mathematician that was so impressed with this, and he wanted to inspire young British women, so he learned Italian to translate her book to English. He made, and that is so noble, and it makes me almost want to tear up. But what happened is there was a curve that she was studying that looked like this, and it's very much like the functions that we're talking about now, but he was learning Italian, and this I think phrase was she using, this was called the turning curve, and this word is very close to the translated Italian of witch, and so anyway, this curve now famously is known as the Witch of Agnesi. And the curve looks like this. And I actually have asked problems dealing with this on Calculus 1 exams, in fact. Okay, here's some more problems for you to do. You want to find each limit. You have two things to do. This one, A, and this one, B. And you know what to do. Let's see how you did. So the big emphasis here is to try to see if you know how to deal with the radicals. And so what you're really doing is x is equal to, well, this says for x greater than 0, you can write x this way. Now, really, the square root of x whole squared is the absolute value of x. So it's x here. So if you're going to infinity, you can go through this calculation. You'll find out that, and you should look at the calculation and understand, but you're dividing top and bottom by the same thing. And so you get that the answer is 3 over the square root of 2. Again, there are no ugly numbers, just like there are no ugly babies. For x less than 0, this is true. Again, if you think about this being the square root of x squared is always the absolute value of x, you get this for free. So dividing both numerator and denominator by x produces this, and you get minus the square root of 3, or excuse me, minus 3 over the square root of 2. And here's the graph. And you might notice that we get a different horizontal asymptote positive and a different horizontal asymptote negative. And there's the graph of that particular function. Here's some trigonometric limits. Please find each limit. You know what to do. let's see how you did. Well, sine just keeps going up and down and up and down and up and down, and it never gets in close to and stays close to a number, so this limit does not exist. The second limit, because sine is bounded between -1 and +1, and you're going to plus infinity in this case, so what happens is we can create this, we divide all the way through by x, I guess is what we do, and since x is greater than 0, it maintains the sense of the inequalities. And now by the squeeze theorem that we studied, our pinching theorem, or whatever we call it in our textbook, you conclude that this is in fact 0. And life is a word problem, and here's a word problem. I worked in industry for a very long time as an applied mathematician, and I never had a boss, man or woman, come to me and say, Jim, we need help solving this equation. They came and said, we have this problem, go help them fix it. But anyway, suppose that this is the level of oxygen in a pond, and it's measured in weeks, and so T is the number of weeks, and so you get this, and what they're trying to do is figure out what happens to the level of oxygen over time. And in fact, I guess I was supposed to ask you some additional questions. So let's just go ahead and look at the solution. So what happens is I was supposed to ask you questions about, like this, what happens after 1 week, 2 weeks, 10 weeks, and so on and so forth. You plug these things in and you find out, oh, there's 50% oxygen, 60% oxygen, 90% oxygen, but the limit as you go to infinity is 100%, and you have to calculate that. And we know that from our theorem, because t squared over t squared is going to be the ratio of the coefficients is going to be 1. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other.